Well, good morning, guys. 2 more weeks.
Good morning.
Don't really have any announcements to make. I am planning on giving your test 5, opening it this Friday, and giving you through Monday at about, I don't know, noon. It will have on it some redox. It will have some electrolysis with Faraday's law. It will have some standard, it will have a redox titration problem. And it will have standard cell notation, which is the new stuff for today. That's what I'm going to go over today, which is tricky. Before I start anything new, I need to know if you've got questions with redox, the term oxidant reductant, diagramming electrolytic cells, specifically polarity of the anode cathode, what occurs at the anode and cathode, and how to use Faraday's law. And also redox titration. Basically, how to go from molarity to normality. Are there any questions before I start new stuff?
Can we do like one redox titration problem just really quick?
Sure. Do you want me just to make up one?
Yes, please.
Okay. How about we do
Could we do the one from the activity?
oh yeah, that'd be a good one.
And also, could you balance the one from the activity, because I did it wrong and I don't know what I missed.
Sure. You know, that reaction's pretty long, so let me just ask this. If I held this up, could y'all see that, or do you want me to, I can write the two things changing bigger on another piece of paper, but let me do that. If you want me to put that paper back up, I will. Let me just do this real quick. Okay, we're going to do it in steps. I consolidated, the first reactant is called ethanol. So I consolidated it as C2H6O. And then the second, the product organic-y thing was acetic acid. I consolidated it. This will allow me to figure out the oxidation numbers. Let me just put them below. Hold on, let me just do it. Okay, so if you work from oxygen and hydrogen, because they're fixed. So I had an oxygen, here's -2. I had 6 hydrogens, that's a +6. So that's making a +4. So 2 carbons have to share a -4, so they're -2 each. Again, you work from oxygen and hydrogen. Carbon is the one changing. This is a -4. That's a +4. So these 2 carbons are 0. Guys, I know that carbons can have different numbers in a particular organic compound, but if you consolidate it like this, you're getting the average of them, and it will still allow you to get the change. Okay, so that changed that carbon. Now this is just part of the reaction. I don't have room on my paper to write all of it. So it went up by 2, but there's 2 doing it. So that's an up of 4. Oxidation, this must be the reductant. Okay, now, the other thing that changed was the chromium. So let me write that down. Again, it's just the species changing because I don't have room on my paper to do all of it. So chromium went from 6 to 3. That's down by 3, but there's 2 doing it, so that's a down by 6. So chromium went from a 6 to a 3. That dropped by 3, but there's 2 chromiums doing it. So that is a reduction. So this is the oxidant. Okay, so I don't know how I'm going to be able to. Okay, I'll try. Once you cross multiply the down by 6 times 2 to get to 12, the up by 4 times 3 to get to 12, your 3 and 2 become your coefficients. A 3 here for this organic-y thing, and a 2 here for the potassium thing. Using these numbers, you can balance the other side, the carbons, 3. You leave your hydrogens and oxygens till the end. Your carbons, you've got a total of whatever, 6 here, so you need 6 there. You've got 4 potassiums, so you need, where is it? 2 of the K2 here. You've got 4 chromiums, so you're going to need a 2 here. And that fixes, if you look at the sulfates on the, whatever that side, right side, how many sulfates is that total? Let's see, 6, 7, 8. You need 8 in front of the sulfuric acid. Okay, so atomically, your carbons, your potassiums, your chromiums, and your sulfates are balanced. What's not balanced are your oxygens and your hydrogens. So it really doesn't matter if over here you count up all your hydrogens here on the left, and then you subtract out the hydrogens here, you're going to need 22 more. So that's 11 waters. And then your last check would be to balance your oxygens. Did that help at all, guys?
Yes.
Okay.
Yes.
Okay, the number one main, most of you got the reaction balanced. I think only one person missed the oxidant reductant part. Naming, y'all did great, except for, this was commonly missed. Let me write the compound down. And then I'm going to go ahead and write the name, because this was missed by a lot. That product is called chromium Roman numeral 3 sulfate. And because it had an AQ by it, it is soluble. Yes, it's not obeying the +1 -1 rule, but if you looked at your solubility rules, that sulfate is soluble. There are only a certain number of sulfates that are not soluble. So because this was a soluble salt, it is a strong electrolyte. So let me go back to, because that was commonly missed. I think that was the only thing missed in that section, was the naming of chromium 3 sulfate and the fact that some of you thought it was a weak electrolyte. It's a soluble salt. Now, I guess I'll set it up on paper. Hold on. To get the molarity, they give you, oh, this, by the way, this, let me let this person in. This is a famous reaction called the breathalyzer test. They used to, and I think they still do, if you are pulled over and they suspect you for drinking, they can get you to breathe in a tube, And if you have alcohol on your breath, the chromium changes colors in the tube from the 6 to the 3. And if it changes colors, then they know that you've got alcohol on your breath, or that you've had, and then they do the blood test also. Hold on, guys. I'm sorry. Let me check these people that came in. Okay. Let's see, where was I? Oh, to get the concentrate or the molarity. Let me write it out on my paper. That's another thing that y'all missed, especially the molarity to normality, but I'm getting ready to write it out because you will have a redox titration problem on this test.
You said the test is going to be next Monday?
That's when it closes. I'm going to start it Friday.
Okay.
Yeah, I'm going to work on it tomorrow. Okay, most of you got, some of you missed this, but this is, if you take your 0.025% by volume, which is 0.0, and I tell you what it is, it's 0.025 grams per 100 milliliters. This was the molar mass, okay? And then you know 1,000 milliliters to the liter, so that was your molarity. Now, this is for this compound. And this compound, sorry, let me, oh, it just got ink all over me. So down by 3 times 2. Sorry, this smeared, it's all over my hand now. Chromium went from a 6 to a 3. That drops by 3, but there's 2 chromiums doing it. That right there is the equivalence per mole. If you know your molarity here where my finger is, you just multiply that by 6 equivalents per mole to get the normality. So some of you missed that. Is that good, guys, for going over that problem? Yay or nay?
Yes, thank you.
You're welcome.
I was wondering why it's 6 equivalences.
Okay. Hold on. Where is it? Do you understand that chromium is a +6 in this compound?
Yes.
Do you understand that it's a +3 in this compound?
Yes.
It dropped by 3, didn't it?
Yes.
But there's 2 chromiums in this compound. You had to multiply by 2. That's where it's 6.
Okay.
Why doesn't it, why don't you divide by 2 when it's going to XCR2 also?
You're always looking at the change for the oxidant or reductant on the left side. You're not looking at the right side at all.
Okay.
Okay. And I guess I didn't write the, here, let me do that on this paper. I didn't write out the step. Okay. If you know a molarity and you're just wanting to cancel the moles, the 6 is the change number by the total change number, and that unit is equivalents per mole. So you're looking at the, you're only looking at the oxidant or the reductant in a titration problem. Okay. Anybody else have a question like on Faraday's law? Here are the steps for Faraday's law. You convert your time, because it could be days, hours, minutes, it could be weeks, I guess. Convert your time to seconds. You multiply that time in seconds by your current given in terms of ampere. Ampere seconds, you multiply together, you compare it to that constant, which is 96,500. When you divide your ampere seconds by the 96,500, your final unit is called a Faraday, which is an equivalent. You finish the problem by either multiplying by the equivalent weight, or you can convert it to moles and then use it in a gas law if you want to, or use the 22.4 liters per mole, but that's the gist of how to do Faraday's law problem. I did create, before I do the new today, I did create another diagram, if you will, where we're labeling it, and then a Faraday's law that goes with it. So let's do that, and that will sum up electrolysis. Now, I'm thinking about, I have a beaker. In my beaker, I have some zinc nitrate in water. I have that. So I have some zinc ions, zinc 2, I have some nitrate ions, and I have some water. I have 2 electrodes. Around one electrode, I'm noticing a metal plating out. Well, that makes sense because I taught last time the cathode attracts cations, and that's called reduction. So right here, the zinc 2 is being reduced. Oops, did I? Okay, yeah. Forming zinc metal. Okay. On the other electrode, I notice bubbles. And it can't be due to nitrogen. If the zinc is being reduced, the only thing nitrogen can do, if it's a +5 here, is go down, which is reduction, but you've already got something being reduced. So the nitrate ion is doing nothing. That no means not involved. It ends up being a spectator ion. Oh, hold on, let me admit. It ends up being a spectator ion, and so I have my water must be undergoing oxidation. The water in my beaker is producing oxygen due to the battery. The electricity is forcing water to do this. You balance atomically your oxygen. You have 4 hydrogen ions here to cancel your 4 hydrogens here. And then you need your electrons being lost, and that's proving oxidation. So your overall reaction, since you've got 4 electrons here and you only have 2 here, you have to multiply this whole thing by 2. So I did that here, and this where my finger is would be the net. Now, the question usually would be, well, where did the nitrate go? Well, if nitrate was here, the acid produces nitric acid over here. The nitrates cancel. Now, let's think about this. Zinc, if we flipped that reaction, zinc is a metal that would react with an acid and produce the salt, aqueous salt. The reason why it's producing the oxygen and not hydrogen gas, it has to do with this cell potential table that I'm going to show y'all today. Okay. Anyway, so that's my diagram. This is my net. Now, here's the math that goes with it. Same reaction. I'm going to read it and then I'll hold it up. What mass of zinc may be collected if I supply a current of 2.750 amps for 13 hours and 25 minutes? So my first step. See, here's my word problem right here. I change my 13 hours to seconds. I change my 25 minutes to seconds. I add them up. I multiply by the amp. I then compare that number to the 96,500, and I get my Faraday's or my equivalents. But I want to know what mass. So I take my equivalents, and I know that 1 mole of zinc 2 has 2 equivalents, because this was the half. Here, let me show that half reaction again. Here's where the 2, right here. 2 equivalents per mole, or you can go from 2 to 0. That's a change of 2, and that's equivalents per mole. So I know my equivalents, 1 mole over 2 equivalents. I get my moles, and that's must be the molar mass, so I can figure out how much zinc in terms of grams is collected at that cathode. Okay, questions with that? Now, I gave you guys a practice that had on it, I'm looking at it now, let's see, two Faraday's law problems and 2 diagrams. And then it also had another redox titration problem. When I emailed this, did I email you guys the numerical answers? Felicia, did I email the numerical answers to this practice?
I think you had the answers in red,
Okay,
the same document.
yeah, okay. Okay, are there any questions before I show you? That was electrolysis or an electrolytic cell. Electrolysis is a 1 compartment cell. Voltaic or galvanic cells are 2 compartment. So they're going to look different. But on your final exam, you don't really have to draw the diagram picture that I'm getting ready to show. We show the student how to write that diagram in 1 line. Example. Okay, this is now called voltaic or a galvanic cell. It's 2 compartments. It still has 2 electrodes. It does not have a battery or direct current. Instead, this V stands for voltmeter. Because what's going to happen, this chemical reaction that's going to occur is going to produce electricity, so it's spontaneous. The electron flow is still anode to cathode, just like the other cell. However, the polarities flip to a much more natural assumed charge. Electrons want to move away from a negative, and they are attracted to a positive. Now, to complete this circuit, you need something called a salt bridge. And the salt bridge, for your car battery, your salt bridge is your sulfuric acid. Now, if I was doing this in the chemistry lab, I could get a beaker of, say, a zinc salt in water and a zinc electrode, and then a copper salt in water, so soluble salts, and a copper electrode. I could get me a paper towel, scrunch it up, put it in salt water solution, bring it out, wring it, but it's still wet with salt water, and dangle it over my 2 beakers in the solution. I would connect my voltmeter using alligator clips to my metal electrodes, and this is going to read a number. It's going to read whatever. I just created a chemical battery. Okay, now I think, let's see what did I do the zinc one? Oh, I did. Okay, it's coming up. But before I show you the actual number, this picture here can be represented in 1 line. Now, this is how you do it. An electrode goes outside. These little bars here stand for electrode touching solution, electrode touching solution. So the solution is going to be some molarity. This double line here stands for your salt bridge. So in a minute, you're going to notice that I'm going to put in my 2 electrodes, whatever they are. Well, it's going to be zinc and copper. This will be my zinc salt solution at probably 1 molar. This will be my copper solution at 1 molar. And I would draw, depending on the electron flow, if I want this to be the anode here, if I want zinc to be the anode, you draw your electron flow over your salt bridge to tell you anode to cathode. So, hold on. Oh, well, yeah, let's just do it. So here's my example. I went ahead and I put my zinc here. So, oh, I didn't draw. Oh, it's on the next sheet. Okay, so this is my picture. Zinc electrode, zinc solution, 1 molar. Copper electrode, copper solution, 1 molar. Salt bridge, voltmeter, good. I look up what are called standard reductions for both. And how I know they're reducing or reduction, 2 goes to 0, 2 goes to 0, so it goes down. I look up these numbers, or they are provided to you guys, and I'll show you in one of my PowerPoint slides where I got these numbers. Now, you keep the more positive one as reduction. I'm keeping this, so this becomes my cathode. And you write it as reduction. You flip the other one. If you flip the other one to show oxidation, you must change the sign. So my battery, the E stands for electrode potential. Voltage is the unit. So my cell battery is simply the oxidation number plus the reduction number. And I just created a 1.10 volt battery. When you get a cell potential that's positive, that is a spontaneous reaction. Now, here is how, see all this picture, all this mumble jumble up here. All you have to do is write it in one line. One line. Zinc on the outside, copper on the outside. Zinc 2+ at 1 molar, because those are standard conditions to use 1 molar. Copper 2+ 1 molar. I'm drawing my electron flow from anode to cathode over my salt bridge. If you use 1 molar, those are standard conditions. Let's see what I have on the bottom. Okay, so, okay. And then I have a little note here. What if we give you a half reaction that doesn't involve a metal? Then you're going to use platinum as one of the electrodes, because platinum is inert. It's not a very reactive metal. It's below hydrogen on your activity series. So we use platinum as the means to conduct the electricity. Now here's my example. Here is my example. Let's say I have this reaction going on, permanganate ion going to manganese 2. That's a 7 to a 2. That's a drop reduction of 5. But there's no, in my half reaction here, there's no Mn metal. So I have to use platinum. Here, I have aluminum 3 to 0. That's a drop of 3. So they're both reductions. Both of these numbers here are reductions. You keep the more positive one. Let that be the cathode. Flip the other one. Let that be the anode. So now my electron flow must be this way, right? Because you have to go anode to cathode. So you would add, okay, if y'all need me to put these sheets back up, I will. Here. So I kept this as my cathode reduction. I had flipped this one, so this is my anode oxidation. My electrons don't match. I cross multiply, distribute through, okay? And to get what my battery is, I take my reduction plus my oxidation, the one I kept, and I had flipped the sign here. I just created with this reaction a 3-volt battery.
I have a question. How do you know which one you flip?
You
said
keep,
the one that-
you're given 2 reduction numbers. You always keep the more positive one as the cathode. You flip
Okay.
the other one.
Okay.
Yeah.
And there was a negative number. Isn't that like, I got confused with that because there was a positive and a negative number,
Okay.
and you said they're both.
Reductions. Here's why.
How do we know that?
Okay. I'm going to write it on another piece of paper because that one's too busy. When I give you, or your book gives you something like this, let me just, well, I'll just do the aluminum one. Okay. When we give you something like this,
Mm-hmm.
we're telling you write it this way. Now watch. Okay. We're telling you left. This little slash means arrow.
Okay.
So it goes down. So if you to balance it, that's now reduction.
Okay, yeah.
So if we give you the number for that reduction was negative 1.66 volts, and we're keeping the other one because it's more positive, then you flip this. So watch, I'll flip it. Let me actually write flip. So this is how I flipped it. Hold on. You flip it to make it now oxidation. Here.
So from this step, okay, and it's reduction, but it's gone down less than the other one? Or how?
I taught last week here. Hold on. Here. If aluminum's here at +3 and it goes to form its element.
Yeah, I know. Yeah. That is clear, but I'm asking like compared to the other reaction we had.
The other one's reduction too. Here, let me just, but
yeah, like
you can't
what's the
have,
difference between them then?
what's the difference?
Yeah.
Okay, hold on. Okay, the other one had, here, let me write what it had on the paper. So it had MnO4 minus / Mn2 plus. On the other side, it had this. Left, arrow, right. Now, how did I know that's also reduction? Well, you write the numbers. 7, drop to 2, down. Down.
Oh, 7. Oh, okay, of course.
Yeah, you don't go by the minus.
Yeah, I got confused with that. Okay.
But, you know, you can complete that reaction. You would put 4 waters, and then you come over here and put 8 hydrogens, and then you do 5 electrons.
So that one's going down. So that one's going down.
They're both going down.
5.
But they're both going down, but you can't have 2 reductions in a overall reaction. So here your
So
choice.
you take the one that has gone down more?
You keep the more positive number. So back to my here. These are both reductions.
Yeah.
You keep the more positive number. You flip the other one. If you flip this, you changed it from reduction to oxidation.
Oh, okay. Okay, now I understand.
Do y'all want me to do, well?
Those are numbers from like a data table.
Right. No, they're okay. Let me share the screen here. Just I don't know that I have them all. Let's see what I have. In the PowerPoint slides I sent you guys, we don't have them all. Okay. What do y'all see in common? These are called standard reduction potentials. Oh, there is a table, 18.1 in your book. Okay, this is part of one. This is a slide. Do y'all notice that these are all plus electrons? Gain of electrons? So this top one, if I wanted to show this in on my paper, like the chlorine, I would write E, the superscript. Let me just write it and then I'll show you. There. I would write it chlorine diatomic on the left, arrow that slashes the arrow, chloride. So if I'm right, and then I give you, notice that number on that slide is 1.3. Oh, y'all can't see my paper, can you?
We
y'all
can
see?
kind of on the side, or I can at least.
Yeah. Okay. Well, let me finish this out, and then I'm sorry, I forgot that that's. Okay. Let me write another one. Let's do the cadmium one. And the cadmium's negative 0.40. So that's, oh, this will be good that I'm doing this, maybe. Okay, I'm going to stop the share of this. Okay, based on that table that I just showed, the standard reduction potential of chlorine going to chloride was this positive number. So that's this, right? Reduction. The standard reduction potential for cadmium 2 to cadmium metal, was this negative number. Now, these are both reductions. You keep the more positive number and flip the other one. If you're flipping the other one, you've just changed it. It's no longer reduction, it's now oxidation. So I'm gonna flip it. So I'm keeping the chlorine one. So I'm gonna write keep the 1.36 volts, and then I'm gonna flip. So let me write the reaction. I know this, golly, I just wish we were in a classroom. Flip the cadmium one. So this is plus 0.40 volts. So now it's okay. So I kept the more positive number and I kept it as reduction. I flipped that negative value to positive and I flipped my reaction so that it's oxidation. You add them up. Well, it happens that these electrons cancel. You add these up. Oh, even if you cross multiplied here, you don't multiply these numbers. You never mess with the standard potential numbers. So the cell, so the E superscript of the cell is the oxidation value plus the reduction value. So that was 0.40 volts plus 1.36 volts. So that's 1.76 volts. So it's almost a 2-volt battery. And then you add your reactions up. So you have cadmium reacting with chlorine gas to make cadmium 2 plus or 2 Cl minuses, or, you know, it could be this. Yeah. So your overall cell potential. Oh, by the way, if you want a spontaneous reaction, these numbers have to be positive. They always have to be. If you, let's say you did the math and you get an overall negative number, reverse everything. Just reverse the reaction. Okay, anyway, so the cell potential, this is called electrode cell potential, is, these are, the little V's here are volts. So you add the two numbers together. That's what your battery's going to read, what the voltmeter's going to read. I'm sorry, not with the battery, the voltmeter. And then your cadmium will react with chlorine gas and produce cadmium chloride. I know, that's new stuff. I know. I get it. I did talk with Dr. Burns over the weekend. And Mallory's going to understand what I'm saying. I said, can we just not do the Nernst equation? In other words, when we create this final, can we leave the Nernst equation off? And he said, sounds fine with me, but we're waiting for the other colleague to well, she did respond. She goes, well, I always teach the Nernst equation. I said, for 38 years, I've always taught it. But can we just not teach it this semester? Because it's like 2 steps more difficult than what I just went over. So for right now, I'm going to send a practice on it's called standard cell notation. I know on the final, you're going to need to know. Let me go back to that PowerPoint. Hold on. Where is it? This is a typical kind of thing they'll do. They'll give you, say from this lead, this one, the last 4, okay? And then they'll ask, given the table, which one of those would be the best reductant? Now, let's think about this. Which one of these numbers would you keep at the cathode? They're all negative, I get it. Which one would you keep at the cathode? The most positive one, which is this one. If you flipped this bottom one to make it oxidation, this is going to be the best reductant, and this is going to be the best out of these 4 oxidant. Y'all following the concept that I'm saying? Oxidant meant the thing that wants to be reduced. Reductant means the thing that wants to be oxidized. Well, out of these 4 potentials here, the one that's going to want to be flipped the most is this one. Because when you add 1.66 to the other 3, you're going to get a positive voltage, won't you? Are y'all following the concept? That is definitely on your final exam.
As far as wording, when it's like oxidant, is that the one doing the oxidizing or getting oxidized?
The oxidant is the thing being reduced.
But is it the one losing the electrons or gaining?
No, gaining. The oxidant is the thing gaining electrons.
Okay.
Yeah. It's also called, oh, here it is. Well, they call it oxidizing agent. See here, oxidizing agent. The oxidizing agent is the oxidant. The reducing agent is the reductant. Oh, here's another concept. I'll have to put all my papers in it. They're all scattered. It's fine. I can do this. Oh, here, let me get a chart. Here we go. Here's another, oh, let me stop share of this so y'all can see. Okay, here's a periodic table. And I've got my halogens over here, okay? Which halogen would be the best oxidant and why? Now, hint, oxidant means reduced. Reduced means give it an electron. That's my hint. Which halogen would be the best oxidant because it's going to grab that electron more than any other element? Come on.
Fluorine?
Huh?
Fluorine?
Fluorine, because it's the most electronegative. That is a typical concept question. Oh, here's another one. I'm just thinking up a bunch of stuff. Watch this. Hold on, let me write these down and then I'll ask. Separate, but two examples. Both of these have in common, they're very, very good what's? Oxidants or reductants, and why? They're both very good, either oxidant or reductant, and why? Okay, before you answer, let me give you a hint. There. They can only go down.
Oxidants?
Yeah, they're being reduced. See, if you look on your chart, where is it? Manganese the maximum manganese can be is a +7. The maximum chromium can be is a +6. You can't climb manganese, you can't go from +7 to say +9. You can't. So if you can only go down in number, down meant reduction. Reduction means the oxidizing agent or the oxidant. So both of those that I just, wrote, they can only behave as oxidants. Now here, I didn't even finish it out. We could finish it out. Okay, so we've got 4. Here, let me finish it out for you. And you could do the change method on it also, but there. Permanganate can only be reduced. Dichromate can only be reduced. The thing being reduced is called the oxidant. That's a concept that y'all need to know. So I'm going to go through my practices, or maybe I'll look on, I'll do both. I'm going to email you a practice on just standard cell notation stuff. Okay. I'm going to verify with Dr. Burns sometime today. Do we really need to teach the student the Nernst equation? If he says, well, the concept, in other words, we don't need to use the numbers. Even if it's just the concept, they always will provide the Nernst equation on a test. Okay. If you just know what it means and what it stands for, that's probably the only thing that I need to teach y'all. But if he says, hey, let's don't even put anything like that on the test, I'm going to say, great. That would be great. Because the 1120 students would never, ever use it again anyway. So, with that said, are there any questions? My goal today was to show you standard reduction potentials and this little notation. Let me review the notation and then okay. I'm going to do a little circle here. My notation. This is called, oh, by the way, it's called conventional cell notation. Let me write that down. Conventional cell notation. This is what it means. On the outside, the thing on the outside of the single lines are called electrodes. The electrode is in solution at some concentration. This electrode is in solution with its common ion at some concentration. The double lines mean salt bridge. Now, question to the class. If I draw this this way. By definition, what is this? Is this the anode or the cathode?
Anode.
Right. That's right, Jim. And so the other is the cathode. Now, if I drew it the other way, this becomes the anode and this becomes the cathode. Now, last question to the class. Let's say in this beaker over here, let me just write. I'm sorry, this is a mess. Say in this beaker, I have dichromate, chromium-3, and hydrogen ion, which is telling the student, it's telling you guys, here, it's telling you you've got dichromate, chromium, and some hydrogen. It's telling you to use hydrogen in your rules to balance that reaction. Do you see where my fingers are? Any chromium metal? No. So what you're going to use as the electrode here?
Platinum?
Exactly. That's right. So now when you see a conventional cell notation and you see a PT, it's not part of the half reaction at all. Matter of fact, below this beaker, I would write this. I happen to have some of these memorized. And maybe let's go ahead and just put aluminum in this one. Don't care. Okay, I know this is messy, sorry. If I have aluminum as my electrode, and I'm telling you its cell potential is aluminum 3/aluminum, and I'm giving you this negative number. Okay, leave it alone for right now. And then I give you the cell potential here of dichromate on the left going to chromium-3 on the right and giving you this positive number. I have given you both of these in terms of reductions. You keep the more positive one and you flip that one. If you flip that one, you change the direction of that so it becomes oxidation. This is the kind of thing I'm going to email you guys to practice. If you do not have a book, it just said on that PowerPoint, it's in table 18.1 or something like that. Google standard reduction potentials. Now I'm going to give you numbers and I'm going to give you values like this, right? But what I'm not going to give you is how to write the half reaction. So you have to figure that out. Well, it's not hard. This is on the left side, the slash is the arrow, this is on the right side. This is on the left side, the slash is the arrow, this is on the right side. What's going to happen? You're going to have, well, whoa, two of them have they're both being reduced. You're not allowed to have two reductions going on at the same time. You keep the more positive one, you flip the other one.
Does the flipping imply that you're oxidizing like the aluminum of the electrode?
The flipping means the aluminum is being oxidized, yes.
So you couldn't have that on, like, if you have to use platinum, like you have to have the same electrode as mixed.
Right here, that's a good. Oh, where's my sheet? Hold on. This is going to be a good thing that I'm saying. Let me find it. Okay. At the very beginning of today's lecture, imagine we kept the more positive one and we flipped this one, right? We kept the more positive number and we changed the sign of that one. Well, what is this doing? Zinc electrode is being oxidized. Now, just bear with me. This electrode, the copper salt, the cation, is attracted here and it's producing more copper. So this is what it looks like. The zinc electrode is going to disappear, and the copper electrode is getting huge. Okay? Now, question to the class. This is still going on as a battery. This is still reading the voltage, whatever it was, 1.10. Yeah, still a 1-volt battery. What do you think happens when this zinc electrode right here, this zinc electrode completely disappears? Guess what happens? What's the voltmeter going to read when that zinc electrode is all gone? It will read 0 because the battery is dead. And we throw those batteries away because they're not rechargeable.
But how would that work if you had platinum instead of zinc electrode?
The platinum electrode is inert. It doesn't grow, it doesn't decrease, it's just serving to conduct electricity.
But would it if the circuit required that the zinc got oxidized?
If we had, okay, say the zinc is here, and in this beaker, I have a platinum electrode with my dichromate stuff, right? What's going to happen, this is still going to get eaten up, and the battery will go dead. The platinum's not going to have anything on it because the chromium, that chromium reaction didn't produce any metal at all. Does that make sense?
Yeah.
Okay. My goal to send you guys will be, I'm probably going to do maybe one more Faraday, maybe one more redox titration problem, and 4 of these cell notation things. Okay. And then I will ask some questions in concept for each one of those cell notation things, like which one would be the oxidant? What would the voltage be when when you add them up? Write the overall balance reaction. So if you can do those, and I will find out before Wednesday if we need to do the Nernst equation. Questions? Anybody? Okay, so I have one more lecture today, but I may go ahead and start working on the practice to send y'all. My 1110 people, we're just doing gas laws this week. So I'm not sending them any more homework until maybe Friday. And it'll be, Felicia, if they're asking or they ask you, it's just going to be that phase diagram and phase change and intermolecular forces.
Okay.
That's the only new thing I lack in covering for 1110. For the 1120 people, we may be done. Oh, and I sent you both of those practice exams, and I made the keys. I worked out little notes on mine. Some of the problems, it's hard to read the superscript. So maybe by Friday, have them where you can look at them, and I will say, guys, I'm making up something. Guys, on number 38, it's a 10 to the minus 18. Because, it's hard to read some of those. So I will, maybe on Friday, I'll go over like the ones that are hard to read. Anybody else have a question?
Are we able to do any Saturday sessions on Zoom? Just throwing that out there.
Oh God. Yeah. Well, you know what I do on the weekends?
Mark stuff.
Yeah, it's called grading.
Yeah.
It's all I can do to stay caught up with 5 lectures. y'all start, as you're studying, Kevin, as you're studying, just start jotting down notes. My hope is next week, every time we meet, I'm just going to answer your questions. And it can be on these practice tests. It can be like, y'all can go back to your 1110 stuff and say, you know, actually, and I haven't even seen the final yet. I don't know what's on it. I know it's going to have 1110, and it generally is half of it's 1110 and half of it's 1120. But because we have control in selecting certain questions, I'm hoping we can take the Nernst equation off, any of the thermo stuff off, and we can have control on, I mean, less is more, in my opinion. Let's just do the basic stuff. You know, let's ask them the symbol for sodium. If they get it right, they got a question right. I mean, that's what I want to do. Anyway, we can get through this. We just have this week and next. And I have no idea where that final exam will be placed. I have a feeling it'll be on D2L. And I want it to be only 50 questions. Mallory, when she took it, there were 70 or 75 questions on that test. I'm for, let's just do no more than 50. Give them the hour and 50 minutes and call it a day. And as soon as I see the exam, I can't tell y'all exactly what's on it, but I'll do stuff like, well, you better know your intermolecular forces. You better know how to do a limiting reactant. That's what that's my hope. So I'm hoping to see it this weekend, so that next week when we meet, we're just reviewing. Your test number 5 will be, I'll open it up on Friday, and you'll have through like Monday to complete it. I haven't created it yet. So my goal right now is I have to create this practice for y'all and email that like today. Anybody else have a question? Let's see, there's 18. Okay, I'm missing one person. Let's see, who could that be? Is Jordan here? Okay. Jesse Osborne? Matthew? Oh, there it is. Found it. Ebby's here. Another question, or any question?
This is unrelated to chemistry at all, but do you know what happened to Nick?
No, I don't. Does somebody in the class know what happened to Nick? No. There are quite a few. Well, like Laura. What happened to Laura? I don't know. I don't know. Are any of y'all taking summer classes online?
I might.
Okay. Let's see who this says. Oh, well, good luck. Everybody, good luck when you're taking online stuff this summer.
Thank you.
I wish you the best. Morris here is not teaching in the summer. I'm surviving this, but no, I'm not going to go through this hell again. No. Okay, well, Felicia, thank you for recording. You can stop the recording.